All right, everyone, welcome back to SE446. In our previous sessions, we focused on Spark's fundamental data abstraction, the Resilient Distributed Data Set, or RDD. While RDDs are the foundation of Spark, working with them directly can be complex, especially for structured data. Okay? Today, we will explore a higher level, more intuitive, and highly optimized API, the Spark data frame. Many of you who have used the Pandas library in Python will find the concept very familiar. We will see how Spark extends this tabular data model to a distributed environment. Our lecture will cover the journey from RDDs to data frames, how to create and transform them, and then we will dive into the powerful capabilities of Spark SQL and its underlying Catalyst optimizer. Let's begin. So here is our roadmap for today's lecture. We will begin by understanding the motivation and the transition from the low-level RDD API, which we have already covered, to the structured world of data frames. This will help you appreciate why data frames are now the standard API in Spark. Following that, we will get into the practical aspects, how to create data frames from various data sources and how to apply common transformations to manipulate the data, much like you would with the Pandas data frame. A significant part of our discussion will focus on Spark SQL, which allows you to run familiar SQL queries directly on your data frames. We will then look under the hood at the Catalyst optimizer, the engine that makes all of this so performant. Finally, we'll cover how to write your results back to storage and conclude with a practical guide on when you should choose to use a data frame versus an RDD in your projects. Let's get started with our first topic. So, as we begin our journey into this new abstraction, our first section, from RDDs to data frames, will establish the core motivation. And we will ask the question, what were the limitations of RDDs that necessitated a new approach? We will see that RDDs lack schema and optimization, which can make them cumbersome for structured data. Following this, we will dive into the practical mechanics, covering how to create data frames and apply various transformations, which you will find is quite similar to working with Pandas. We will then explore the power of Spark SQL before looking under the hood at the Catalyst optimizer, which is the engine that provides significant performance gains. Finally, we'll cover writing data and provide a clear guide on when to choose a data frame over an RDD. So to formalize our agenda for today, let's review our specific learning objectives. By the end of this session, our primary goal is for you to understand the data frame API and critically how it improves upon the RDDs we have already studied. We will then move into the practical skills, creating data frames from common file formats like CSV, JSON, and Parquet directly from HDFS, and applying essential transformations such as select, filter, and group by. A very powerful feature we will cover is how to query these data frames using standard SQL. Importantly, we will also answer the question of why. Data frames are faster by examining the Catalyst optimizer. To make these concepts concrete, we will work with the Chicago Crimes dataset throughout our examples. All right. So before we dive into the power of data frames, let us first understand the problem they are designed to solve by looking at the limitations of the RDD API. Imagine we want to process a simple CSV file, like our Chicago Crimes dataset, using a raw RDD. As you can see in the code example on the slide, we would first load the data as an RDD of text lines. Then, to access individual columns, we must apply a map transformation and manually split each line by a comma. The consequence of this approach is threefold. First, Spark has no schema information. For Spark, each record is just an opaque Python object, a list of strings in this case. Second, because it doesn't understand the structure or your intent, there is no query optimizer. Spark simply executes your code exactly as written. And third, this manual parsing is verbose and error-prone. This brings us to the central question. Can we have the power of distributed computing without these limitations? This is precisely the motivation for the data frame API. So The answer to the limitations we saw with RDDs is the data frame API. A data frame is essentially a distributed collection of data organized into named columns, very much like a table in a relational database, or more familiarly for many of you, a pandas data frame. The key difference, of course, is that it's partitioned and processed across a cluster. This structure is what makes data frames so powerful. They are built on top of RDDs, but they add three crucial components that solve the problems we just discussed. First, a schema which gives Spark explicit knowledge of column names and data types. Second, the Catalyst optimizer, which analyzes your high-level query and creates an efficient physical execution plan. And third, the Tungsten engine for optimized in-memory binary storage. As a consequence, data frame operations are almost always faster than equivalent RDD code, because Spark can intelligently optimize the work it needs to do before executing it. So, building on our discussion of the internal optimizations, let's now visualize where data frames fit within the broader Spark ecosystem. As you can see in this diagram, the Spark core, which provides the fundamental RDD API, forms the foundational layer. On top of this, we have the structured data APIs, Spark SQL, data frames, and datasets. This layer is crucial because it provides the schema and optimization capabilities we just talked about. Now, what is important to understand is that this data frame layer is not just an alternative to RDDs. It has become the primary interface for many of Spark's most powerful libraries. For example, MLLib, Spark's machine learning library, which we will cover in week 8, is built directly on top of data frames. Similarly, structured streaming for real-time data processing also uses the data frame API as its foundation. As a consequence, when you are developing new applications in Spark today, the data frame API is almost always the recommended starting point. So, having established the importance of the data frame API as the modern foundation for Spark, let us now outline our journey for today's lecture. We will begin by formalizing the evolution from the low-level RDDs to the structured world of data frames. Following this, we will dive into the practical aspects of creating data frames from various data sources, which will be our main focus. We will then explore the rich set of transformations available and see how we can leverage the power of Spark SQL. A crucial part of this lecture will be understanding the Catalyst optimizer, the engine that makes data frames so performant. Finally, we will cover how to write our results and provide a guide for deciding when you might still need to use an RDD. Let us begin with the first topic. All right, so as we begin our journey into creating data frames, the very first thing we need is an entry point to the Spark cluster. In the older RDD-based world, this was the Spark context. However, for the structured APIs like data frames and Spark SQL, we now use a new unified entry point called the Spark session. Let us look at the code on the slide. First, we import Spark session from PySpark ZSQL. Then, we use a builder pattern to construct our session. We can set an application name using tot laldo app name di which is helpful for monitoring, and pass any specific configurations with Kaukonani and the most important part is the fault tolerant key and path get or create method. This intelligently either creates a new session or returns an existing one, preventing multiple contexts from running. It is important to note that the Spark session encapsulates the Spark context, which you can still access via Spark context if you need to work with RDDs. For convenience, when you use the PySpark interactive shell, this Spark object is already created for you, so you can start working with data frames immediately. All right, so now that we have our Spark object, which is our entry point to the Spark session, the first thing we typically want to do is load some data. Let us understand this through a simple example. Imagine we have a common data format like a CSV file named people@esv, which contains columns for name, age, and city. How do we get this into a data frame for analysis? The process is quite straightforward. We use our Spark object and call the read method. We then specify the format, in this case CSV. We also provide a couple of important options. Option header, true, tells Spark to use the first row as column names. The second option, infer schema, true, instructs Spark to automatically detect the data types for each column. And finally, we call antat load with the file path. However, it is important to note that for production systems, infer schema is not recommended because it requires reading the data twice, which is inefficient. A better practice is to define the schema explicitly using a struct type, which we will cover shortly. All right, so after loading our data, the immediate next step is to inspect the resulting data frame to verify that it was read correctly. The first command we typically use for this is print schema. As you can see in the example for the Chicago crimes data, this method provides a clear tree-like view of our schema. It shows each column's name, its inferred data type, such as integer for the ID, string for the date, or double for latitude, and then whether null values are allowed. This is our primary way to check the structure. To view the actual data rows, we use the show method. By default, it might truncate long columns, which can hide information. That is why the command show5 truncate the false null is so useful. It displays the first 5 rows and ensures that no data within the columns is cut off, giving us a complete picture of our dataset's content during initial exploration. So after inspecting the schema and the first few rows of our data, it is crucial to understand what the data frame truly is at a conceptual level. Let us look at this diagram. On the left, you see the logical representation of a data frame. It looks exactly like a table you would find in a relational database, or more familiarly, a pandas data frame in Python with named columns and rows. However, the power of Spark lies in its distributed nature. As the diagram illustrates, this single logical table is physically broken down into smaller chunks called partitions. Each partition, which holds a subset of the rows, is distributed across different executor nodes in the cluster. This is the fundamental mechanism that allows Spark to process massive data sets in parallel. Unlike the older RDDs, where Spark just saw a collection of opaque objects, with a data frame, it is fully aware of the schema and structure, which enables powerful optimizations that we will explore soon. All right, so now that we understand that a data frame is a distributed table with a known schema, let's discuss how we can actually work with this data. This brings us to the core topic of data frame transformations. These are the operations we use to manipulate, reshape, and clean our data. For those of you familiar with pandas, many of these concepts will feel very intuitive, but the key difference here is that these operations are executed in the distributed, lazy fashion across the cluster. We will start with the most fundamental transformations, selecting columns and filtering rows, which are the bread and butter of data analysis. And let's look at our first example. All right, let's put the concepts of selecting and filtering into practice with some code. On this slide, we see the fundamental syntax for these operations. First, to select specific columns from our data frame, we use the but select method. You can see we are passing the column names origin, destination, and delay as strings. This is very similar to how you might select columns in a pandas data frame and results in a new data frame containing only that subset of data. Next, for filtering rows, we use the pocket filter method, which is an alias for oddaiditam, where here we are filtering for all flights where the value in the delay column is greater than 120. The condition is expressed programmatically using column objects. Finally, we see how to combine multiple conditions. To find flights from SFO to ORD with a long delay, we chain conditions using the ampersand for a and. It is very important to note that each condition must be wrapped in its own parentheses due to Python's operator precedence. This is a common mistake, so please remember this syntax. All right, so after seeing how to select specific rows using filter, let's now look at how we can add new columns or transform existing ones. For example, imagine our flight data has a delay in minutes, but for our analysis we need it in hours. The primary method for this is the with column transformation. The syntax is straightforward. You provide the name of the new column as the first argument and the column expression for its value as the second. If the column name already exists, with column will replace it. Otherwise, it will add a new one. Now, a very important concept to remember, which is fundamental to Spark, is immutability. The with column function does not change the original data frame. Instead, it returns a completely new data frame that includes the transformation. This is why you will always see the convention of reassigning the result back to a variable, for example, df yarashar df with column. We are not modifying the original data in place. We are creating a new one. So after seeing how to add or modify individual columns with column, let's move on to another fundamental operation, summarizing data. Imagine you have a data set of sales transactions from different stores. You might not want to see every single transaction, but rather the total sales per store, or the average transaction value. This process is called aggregation. It is conceptually identical to the group by function you have likely used in the pandas library. First, you group the data frame by one or more columns using the group by method. Then you apply an aggregation function to compute a summary for each group. As you see here, Spark provides many common functions like count, sum, avga, mean, and max, as well as more advanced ones like count distinct or collect list. So after performing an aggregation, what does the result actually look like? Here we have a visual example using the Chicago crimes dataset. This bar chart shows the frequency of different types of crimes. As you can see, some categories like theft and battery are significantly more common than others. This insight was generated with just a single line of chained operations, which you can see on the slide. First, we use df.groupBy primary type to group all the records by the crime category. Then we apply the book.count function to get the total number for each group. Finally, to make the chart more readable, we use order by desk count type to sort the results, placing the most frequent crimes first. This is a very powerful and common pattern in data analysis. After performing aggregations to understand patterns within a single data set, the next logical step in many data engineering pipelines is to enrich our data by combining it with other sources. Let us consider a practical scenario. Our crime data frame has a district column, which is just a number. Imagine we have another much smaller data frame. Let's call it district df that maps these numbers to actual district names. To create a more meaningful report, we need to combine them. This is done using a join, which is conceptually similar to a SQL join or a merge in pandas. However, in a distributed system, joining two large data frames is an expensive operation that triggers a network shuffle. As a consequence, to optimize this, when one of the data frames is small, we can use the broadcast function. As you can see in the code, by wrapping our small district df with broadcast, we are telling Spark to send a complete copy of it to every worker node. This allows the join to be performed locally on each machine, which avoids the costly network shuffle and significantly improves performance. So after understanding how to optimize a join using the broadcast function, let's now systematically review the different types of joins available in Spark. The concepts here are identical to what you would find in standard SQL or in the pandas library. The diagram on the slide illustrates these concepts visually. An inner join, which is the default, returns only the rows with matching keys in both data frames. A left outer join returns all rows from the left data frame and the matched rows from the right. The right outer is the inverse of this. A full outer join returns all rows when there is a match in either the left or right data frame. Finally, a cross join returns the Cartesian product. The table provides the specific PySpark keywords you'll use, such as inner, left, right, outer, and cross. All right, so far we have been manipulating our data frames using a programmatic object-oriented approach with methods like select, filter, and join. However, a very powerful feature of Spark is its ability to let you query these same data frames using standard SQL syntax. This is incredibly useful, especially in teams where data analysts might be more comfortable with SQL than with Python or Scala code. To enable this, we first need to make our data frame accessible to the SQL engine. We do this by registering it as a temporary table, or more accurately, a temporary view. The most common method is create or replace temp view. This function gives our data frame a name that we can then reference in SQL queries, but it's important to note that this view is scoped to the current Spark session. As soon as the session ends, the view is gone. For more persistent needs within a single application, there is also create or replace global temp view, which creates a view visible across all sessions, which you would then query using a special global temp database prefix. All right, so let's look at the practical implementation of what we just discussed. On this slide, you can see the code for registering these views. First, we have create or replace temp view. We take our data frame, let's call it df, and we invoke this method, passing a string as the name for our view, for example, people. This name people now becomes a temporary table that is only accessible within the current Spark session. Once the session terminates, this view is lost. On the other hand, we have create or replace global temp view. The syntax is identical, but its behavior is different. This creates a view that is visible across all sessions within the same Spark application. It is important to note, however, that to query a global view, you must use the global temp database prefix. So your query would look something like select from global temp people. For most of our use cases, the session scoped temporary view is what we will be using. Now that we have created a temporary view, let us explore the two primary ways we can query our data in Spark. The fundamental point to understand is that both the data frame API and Spark SQL achieve the exact same result. As you can see in the diagram, both approaches are fed into Spark's Catalyst Optimizer, which generates the same underlying execution plan. On the one hand, we have the programmatic data frame API. For example, to find people older than 30, we would write dfbot filter, okay, df age 30. This is an object-oriented approach that many developers find familiar. On the other hand, we can use a declarative SQL query on the view we just created. Spark.SQL select apareça from people where age 30. The choice between them is a matter of preference and team convention. Data analysts often prefer SQL, while software engineers might favor the data frame API. The key takeaway is that there is no performance difference between them. All right, let us continue with more examples to further illustrate the power and flexibility of Spark SQL. In the previous slide, we saw a simple filtering operation. Now, let's consider a more complex scenario, such as aggregation. Imagine we want to calculate the average age of people, but grouped by their gender. Using the data frame API, we can achieve this by chaining methods. We would call dfbot group by gender, okay, afal, to specify our grouping column. Then we apply an aggregation function using egg can key, and inside it we specify avg, the age, to compute the average of the age column for each group. This programmatic approach is very powerful, as you can build complex queries step by step. Alternatively, we can express the exact same logic using a pure SQL query on our temporary view. We would simply write Spark SQL, select gender, avg age, from people group by gender. As you can see, this is standard SQL syntax. Both of these commands will be translated by Spark's Catalyst Optimizer into the same execution plan, so there is no performance difference. So in the last example, we saw that both the data frame API and a pure SQL query are translated into the same efficient execution plan. This naturally leads to a very important question. How does Spark achieve this? And what makes data frames so much more performant than their predecessor, the RDD? To answer this, we will structure our discussion today as follows. First, we will trace the evolution from RDDs to data frames to understand the fundamental shift in abstraction. We will then cover the practical aspects of creating data frames and applying transformations. After that, we'll revisit Spark SQL in more detail. The core of our lecture will be the fifth point, a deep dive into the Catalyst Optimizer, which is the engine that makes all of this high-level performance possible. Finally, we will look at how to save our results and provide a clear guide on when you should choose an RDD versus a data frame. All right, so as we established, the core reason for the superior performance of data frames lies within this component, the Catalyst Optimizer. Let us understand how it works. When you write your data frame code, you are essentially building up a blueprint of your query. This diagram illustrates the journey of that blueprint. Initially, your code is an unresolved logical plan. Catalyst analyzes this plan to resolve column names and types, turning it into a logical plan. The most important step is next, where it applies a set of sophisticated rules to create an optimized logical plan. It then generates multiple physical plans and uses a cost model to select the most efficient one for execution. The key optimizations listed here, such as predicate pushdown, which filters data as early as possible, and column pruning, which only reads the columns you actually need, are what make this process so powerful. Let's visualize exactly how predicate pushdown works with a concrete example. On the left, we see the naive, unoptimized plan. Imagine we want to join a large users table with a districts table, but we only care about users in district 8. The unoptimized approach would first join the entire users table, shuffling all 10,000 rows across the network, and only then apply the filter. This is incredibly inefficient. Now, on the right, you see the optimized plan created by Catalyst. It intelligently pushes the where clause, the predicate, down to the data source. It filters the users table for district 8 before the join. As a consequence, only a small fraction of the data is actually shuffled for the join operation. This simple reordering results in massive savings in network traffic and processing time. And it's a core reason why Spark is so performant. So we've established that Catalyst performs these sophisticated optimizations like predicate pushdown automatically. But a natural question arises: how can we as developers verify this? How can we inspect the logical and physical plans that Spark will actually execute? This is where the explain method becomes an indispensable tool. Let's walk through this simple code example. First, we create a data frame named df by reading a Parquet file. Next, we apply a filter, keeping only the rows where the value column is greater than 3. Finally, and most importantly, we call df.explain. The output you see is the physical plan. Notice the line that says pushed filters. This is the direct evidence of Catalyst pushing our filter condition down to the data source, exactly the optimization we just discussed. This powerful introspection is impossible with RDDs, where arbitrary Python lambdas are essentially a black box to the optimizer. All right, so we've seen how Spark and the Catalyst Optimizer can efficiently process and transform our data. But once we have our final data frame, the logical next question is, how do we save it? This brings us to our next section on writing results. Let's look at the process for writing a data frame to a persistent storage system like HDFS. The API is quite elegant. We start with our data frame, df_fig, and access the write attribute. From there, we can chain methods. First, we specify the file format using .format, for example, the Parquet or ESV. Next, and this is very important, we define the save mode with .god mode. As you can see in the table, overwrite will replace any existing data, append will add to it, ignore will do nothing if the path exists and the default error if exists, prevents you from accidentally overwriting your work. Finally, we call save with the HDFS path. This simple declarative syntax is how you persist your results for downstream applications. Let us now look at a concrete example of this in action. The table on the slide summarizes the save modes we just discussed. Overwrite will replace any existing data. Append will add new rows. Ignore will simply do nothing if the path already exists, and error is the default to prevent accidental data loss. In the code snippet, you can see how this is applied. We take our data frame, df, and initiate the write operation. We then explicitly set the mode to overwrite. As a consequence, if the target HDFS directory already contains data, Spark will delete it before writing the new results. Finally, we use the parquet method, which is a convenient shortcut for specifying both the format and the HDFS path. This single declarative line is how you persist your final processed data back into HDFS. Now, in the last example, we specifically chose the parquet format. This raises an important question. Why parquet and not something simpler like CSV? This diagram illustrates the fundamental difference. On one hand, you have row-oriented formats like CSV. They are human readable, but to access a single column, Spark must read the entire row. On the other hand, we have columnar formats like parquet. As you can see, the data is organized by column. This means if your query only needs the price and quantity columns, Spark can read just that data, skipping everything else. As a consequence, for analytics and any Spark to Spark workflow, Parquet is vastly more efficient, it is compressed, and it stores the schema within the file, which avoids the need for schema inference on the read path. So we have just seen how a structured storage format like Parquet can dramatically improve performance by allowing Spark to understand the data schema. This raises a fundamental question. Can we bring this same level of structure and optimization into our Spark code itself, not just the storage? The answer is yes, through the dataframe API. In this lecture, we will systematically explore this evolution. We will start by moving from RDDs to data frames, then cover their creation and transformation. We will then see how Spark SQL leverages this structure and demystify the Catalyst optimizer that makes it all so fast. Finally, after covering how to write results, we will provide a clear decision guide to help you choose the right tool for your specific problem. So this brings us to the central question in this section of our lecture. When should you choose an RDD, and when is a data frame the better tool? This table provides a clear guide for that decision. Let us examine the key differences. On the one hand, RDDs are schemaless. They treat your data as opaque objects. As a consequence, Spark cannot optimize your code. You are in full control, which is powerful, but means performance is entirely up to you. This makes them suitable for unstructured data, like raw text or complex graph structures. On the other hand, data frames enforce a schema with named and typed columns, very similar to what you know from pandas. This structure is the key that unlocks the Catalyst optimizer, allowing Spark to dramatically improve performance, often making operations 2 to 5 times faster. Therefore, the rule is simple. If your data is structured or semi-structured, if it looks like a table, always default to using a data frame. To make this comparison more concrete, let us look at a practical example. Imagine our task is to count crimes per type from a data set and sort them in descending order. Here on the left, you see the RDD implementation. It requires us to manually parse each line, map it into a key value pair, then use reduce by key to sum the counts, and finally sort the results. It is quite verbose. In the middle, the data frame API is much more declarative. We can simply group by the primary type column called count, and then order by the count in descending order. This should feel very familiar to those of you who have used pandas. Finally, with Spark SQL, it's a standard SQL query. This table summarizes the key differences. The RDD approach took 14 lines of code, whereas the data frame and SQL versions took only 7 and 6. More importantly, because data frames and SQL are schema aware, they can leverage the Catalyst optimizer for performance gains, which is not possible with RDDs. So, to bring everything together, let's recap the journey we've taken in today's lecture. We began by understanding the fundamental shift from RDDs to data frames, recognizing that data frames provide a structured, tabular abstraction with significant performance advantages. We then moved into the practical aspects, covering how to create data frames from various sources like CSV and JSON. Okay, a significant portion of our discussion was dedicated to data frame transformations and actions, which are the core tools for data manipulation. We also explored Spark SQL, which offers a declarative way to query this data. We briefly looked under the hood at the Catalyst Optimizer, the engine that makes this high-level API so efficient. Finally, we covered how to write our results and provided a decision guide for choosing between RDDs and data frames. This gives you a complete picture of the data frame API. So, as we conclude our discussion on Spark data frames, let's crystallize the most important points to take away from this lecture. First, remember that a data frame is fundamentally a distributed table with a schema. While it is built on top of RDDs, it brings significant optimizations. Our entry point for all these operations is the Spark session, and we load data using the spark.read interface and manipulate it using a rich set of transformations like select, filter, and group by. Alternatively, we can use Spark SQL by registering a temporary view. It is crucial to understand that both the data frame API and Spark SQL produce identical, highly optimized execution plans thanks to the Catalyst Optimizer. As a consequence, your choice between them should be based on readability, not performance. Finally, for your pipelines, always consider Parquet as your preferred storage format. This brings us to the end of our introduction to the data frame API. Now that we understand how to manipulate structured data, our next focus will be on execution and application. Next week, we will start by looking at how to run these jobs on a real cluster using Spark Submit with Yarn. We will cover critical performance tuning techniques such as caching with odd persist and optimizing joins and partitions for efficiency. Then, in the second half of the week, we will shift our focus to machine learning at scale using Spark's MLlib. You will learn how to build a complete ML pipeline from feature engineering to training a classifier on our Chicago dataset. All of this will prepare you for your upcoming assignment, which integrates everything we've learned so far.